We are just about ready to move into the calculus portion of this course rather than the more pre-calculus stuff that we've been doing up until this point. So really, this is more like the Calc 1 portion of the course. This is where we're going to start doing derivatives and whatnot. However, before we get to limits and derivatives and all of that good stuff, we need to start by talking about functions of multiple variables. So I will ask you to recall with me the idea behind a function. So back in our old classes, pre-calculus and algebra and whatnot, this was the most common notation that we used for a function. So f was referred to as the function name. X was referred to as the independent variable. And y was referred to as the dependent variable. We would always say that the value of y depends on the value of x. That's what makes it the dependent variable. Now, more generally, this could be referred to as a function of one variable. When we say f of x, this is a function of x. X being the only variable over there, this would be a function of one variable. Now, the idea is, for a given input, there is only one possible output. So, another definition would be a function of two variables. Now, when we refer to a function of two variables, we've now made the jump from 2 dimensions into 3 dimensions. The x and the y each have their own dimension associated with them. One input yields one output, giving us 2 total quantities. For a function of 2 variables, the most common notation that you'll see for this is that z will be a function of x and y. Once again, f is referring to the function name, so that doesn't necessarily have to be the same. Z is referred to as your dependent variable, and x and y are your independent variables. Now, x and y are independent of each other as well as independent of z. An example of something that could be a function of 2 variables, I always love referencing back to this to remind everybody that once you get a career, you look back at your jobs and you say, man, I love my career so much more than I love my job. When you're ordering a pizza, I used to work in pizza. Most commonly, the cost of that pizza is going to be a function of 2 variables. This is assuming that you're calling one place. So the 2 things that this will typically depend on will be the size of the pizza. Fun fact for you, when you're ordering the size of a pizza, it's usually based off of the diameter of the pizza. So a 12-inch pizza, for example, is a pizza with a 12-inch diameter. T will be the number of toppings. Now, of course, we can poke holes in this and start talking about gourmet toppings versus non-gourmet toppings and whether or not extra cheese counts as a topping. But regardless, this is usually what you're going to see as far as a function of 2 variables is concerned. Now, if we wanted to up the ante on this, we could also talk about a function of 3 variables. The most common way that we see a function of 3 variables represented is that x, y, and z all become independent variables, and w becomes your dependent variable. With, once again, f being your function name. An example of a function of 3 variables is you could consider the temperature in any room as a function of position. For example, the temperature, if you're closer to my air conditioning output as opposed to right up next to my ceiling as opposed to right near the surface of my skin, they're all probably different temperatures. More generally, a function of n variables would probably take the form f of, we'll just refer to all of your independent variables as x's. Usually a good way to count to n is by saying 1, 2, skip a few, n. Then whatever you feel like using for your dependent variable, that doesn't really matter. Now, generally speaking, when you have a function of n variables, the thing that you're creating is n plus 1 dimensional, where each one of your independent variables has a dimension associated with it, and your dependent variable has something associated with it as well. Now, that can become very difficult to visualize. For example, that means that a function of 3 variables would be a 4-dimensional thing. Well, we don't really have more dimensions to work with outside of 3 in the real world, so what exactly does it mean to be 4-dimensional? Well, it means that there is a range of values that depend on 3 other values that are given to you, nothing more. Or more generally, if we wanted to go for, n variables, this would be n plus 1 dimensional. Now, I did have some confusion about exactly how to represent something like this when I was learning about it back as a student. I had somebody describe it to me this way. When you talk about a function of 2 variables, you have something associated with x and you have something associated with y. But really, this x-axis is just the real number system, and this y-axis is just the real number system. Now, once we get into z as a function of x and y, and I just realized that I should have drawn this up here, that's my mistake. When you have z as a function of x and y, the way that we try to visualize this using both an x-axis and a y-axis is by saying we have an x-axis and a y-axis and a z-axis, and they're all mutually perpendicular to each other. However, if you were to lower your eye level so that it's level with the xy plane, then really what you have going on is the xy plane looking kind of flat like this, but the xy plane would be like saying R2. The z-axis would be an additional r. Now I realize that this is going to be a bit of a stretch in comparison to the things that I just did, but for a function of 3 variables, you could think of it in the following fashion. If R3 were able to be laying flat, and then you have an additional r coming out of it orthogonal to all 3 of these dimensions, that would be something 4-dimensional. Or if we wanted to get even more general, we could say that if you can lay Rn flat and then put another r on it, now you have something that's n plus 1 dimensional. I realize that that might be a bit of a stretch for you, but take some time. See if you can wrap your head around this.